Hello, welcome to the NPTEL course on Fundamentals of Composite and Cellular Materials. This is the last lecture of this course, and in this lecture we will discuss about the FGMs or functionally graded composite materials. In the last lecture you learnt about the basics of FGMs, that means the definition of an FGM and the basic properties of FGMs and how the FGM structure can be designed. Those things were discussed in the last lecture. Among the properties we discussed about the hardness, flexural strength and the tribological properties. In this lecture we will cover the basic processing techniques for FGMs. There are several techniques which can be used to fabricate the FGMs, but among them in this lecture we will cover around 5 to 6 topics, which are centrifugal casting, pressureless sintering, hot isostatic pressing, spark plasma sintering, friction stir processing and additive manufacturing. You will see that FGMs can be fabricated by using both melting casting route and powder metallurgy route. As I discussed in the last lecture, FGMs are actually composite materials with a gradual gradation of the structure and composition along one particular direction, and depending upon the combinations like metal metal or metal ceramic or ceramic ceramic, different processing techniques can be used. The main keywords to be covered in this lecture are again FGMs, then the different processing techniques like centrifugal casting, pressureless sintering, hot isostatic pressing, spark plasma sintering, friction stir processing and additive manufacturing. So, this is a recap of the previous lecture which I covered, and here actually we again show that how a typical FGM structure is designed. So, as we discussed in the last lecture, in a normal or in a monolithic composite material, the reinforcement particles or fibers or short fibers or IPC, whatever it is, the reinforcement distribution is homogeneous throughout the composite's thickness and cross section. That means, if we make a cut on the composite's sample, irrespective of the depth of the sample where the cut is being made, the reinforcement distribution should be more or less similar. As we learned already that composite materials are inherently heterogeneous material. That means, if we look into a very small length scale, then there is already or there is always a distribution difference between different regions. But generally the composite materials are macroscopically homogeneous. That means, although there is in a length scale quite small enough, there are distribution differences, but if the length scale of the measurement is much bigger than the microscopic length scale, then the composites are globally or macroscopically homogeneous. However, this homogeneous distribution of the monolithic composites, they have some limitation, because if we want to combine different conflicting properties, for example, if we want to have both high hardness at the surface and good toughness or ductility at the core of the sample, this is pretty difficult to attain, because as we know that the mechanisms or the processes which actually increase the hardness or strength of the material, typically the metallic materials, they typically tend to reduce the toughness of the material, and as a result it is not always easy to actually fabricate such a composite material with having both high hardness and also high toughness. However, if we want or if we can design an FGM material where actually if we can distribute the reinforcement material in such a way that on the surface of the material or at the surface layer of the material there is a high amount of hard reinforcement particles like ceramic particles in a metallic matrix, then that region will have actually high hardness, because ceramics typically have a high hardness, and also because of the large amount of ceramic particles there will be more amount of dislocations in the metallic matrix, and that will also lead to more hardness in the on the surface layers. At the same time, as is being shown in these images, if towards the inner dimensions of the sample or material the ceramic particle content is continuously reduced, then those regions will have less amount of hardness, and as a result those regions will be tougher. And this way FGM actually provides an opportunity to develop a material with a high hardness and wear resistance on the surface, and also good properties like ductility at the core of the material. It is not only these tribological applications, there are also many other applications where FGMs actually provide very beneficial applications. Now, after we had this basic understanding of FGMs, in this lecture we will discuss about some processing techniques through which FGMs can be fabricated. The first technique that we discuss in this lecture is centrifugal casting. So, centrifugal casting, as you will see in this lecture, it is a very simple and cost effective technique for fabricating FGMs, and also one big advantage of this technique is that by centrifugal casting one can actually fabricate bulk sized components. Like you can see that on the right hand side it is a typical component or typical sample which was fabricated by spark plasma by centrifugal casting, and the sample dimensions you can see it's a macroscopic sample, and even samples having weight more than a kilo or something like that, those samples can easily be fabricated by centrifugal casting process. And this process is also pretty cost effective because this does not require very high end equipment, it requires very simple casting equipment which is also being used very regularly for normal metal casting applications, and this is actually a very effective technique for fabricating a graded composite. Now, what is the basic principle of centrifugal casting? If we look at the schematic diagram shown on the left hand side, so the basic fabrication technique actually involves two different techniques combined together. In the first step, as you can see over here, this first step we actually fabricate a metallic melt, that is been done over here, a metallic melt, and inside the metallic melt we distribute the ceramic particles. So, as you can see over here, this blue fluid, as you can see, this is the metallic, this is the one from the metallic melt, and within that these ceramic particles are uniformly distributed typically by stir casting process. So, stir casting, as you know, it is a very simple and effective process for fabricating particle reinforced composites. Although it is a very simple and cost effective process, this process has a limitation that this is typically limited to low ceramic content, say around 10 to 15%, because if the ceramic content is too high, then there will be more amount of there will be high amount of viscosity, and also the ceramic distribution becomes very irregular. So, in this process, in this centrifugal casting process, first we fabricate or first we prepare a melt with uniform ceramic particle distribution, and then the mold for this centrifugal casting, this is the attractive part, or this is the main part for fabricating the FGM. So, as you know, in normal casting we typically pour the after we have made a melt, we typically pour the melt in a static mold, right, and when the melt is poured in the static mold, after solidification you get kind of uniform distribution, although you have, depending upon the size of the container and everything, you may have the chill zone or dendritic zone, whatever, but as such you do not have a kind of a moving mold. But in centrifugal casting, what we typically use, we use a rotating mold. That means, as you can see over here, the mold is rotated around the vertical direction or vertical axis, and then when the particle containing melt is poured inside this mold, because of this centrifugal action and following Stokes law, the particles will be arranged depending upon their density. That means, if the particles have higher density, that means if we have typical like if we have two parameters like the density of the ceramic particles rho p and the density of the metallic particles is the rho m, or metallic melt is the rho m, then if rho p is higher than rho m, that means if the density of the particles is higher than the melt density, then the particles will be actually kind of deposited towards the outer surface, and the inner surface will have less amount of particles. Okay. So, this way the outer surface will be having high amount of ceramic particles and the inner surface will have a low amount of ceramic particles, and this way automatically a gradation of the ceramic particle distribution will be obtained. Now, normally whenever we want to fabricate these composites, so typically as we know that for these composites based upon the melting casting route, aluminum and magnesium based metals are the most common ones, and typically almost all the ceramic particles like aluminum oxide or silicon carbide, silicon nitride, whatever, all these ceramic particles they have higher density than the melt of either aluminum or magnesium, and as a result whenever we fabricate this melting casting, we use this melting casting route or centrifugal casting route for fabricating these FGMs. So, we always have higher reinforcement content on the outer surface, that means these regions will be rich in ceramic content, and the inner surface will be kind of devoid of ceramics or devoid of these hard reinforcements. And also this typically happens because in any casting, as you know, that we always have the pores or air bubbles, and because these are lighter than the metallic melt. So, during centrifugal casting these defects typically they tend to come towards the inner side, and all the reinforcements they tend towards go to the outer side. So, these regions will be more reinforcement, and this region will be more of defects and other pores or whatever. So, as a result we have higher hardness on the outer surface and lower hardness or at the inner surface, as you can see in these micrographs. So, here actually this is a cast iron block with some ceramic reinforcement, and here we see that the outer surface, this is the niobium carbide particles, and this niobium carbide, because niobium carbide has a higher density than cast iron. So, the outer surface, the outer periphery of this cast block will have high amount of niobium carbide. So, this will give rise to a high hardness, while the inner surface or the inner region will have less amount of niobium carbide, and you can also see with these dark regions over here, these are kind of the agglomerated pores which will have a lower mechanical properties. So, this way by centrifugal casting process we can have a very nice distribution of the ceramic particles inside a metallic melt. Now, one big limitation of the centrifugal casting process is that this process is only limited for metal ceramic composites. That means, by centrifugal casting process we only obtain a composite or a FGM where the ceramic particles are distributed in a metallic melt. Definitely we can also have a metallic particle like a high melting metallic element in a low melting point matrix, but typically this is always involving a melting casting route. Now, another process which has often been used for fabricating FGMs are basically powder metallurgy processes. So, powder metallurgy routes have different variations which can be used for fabricating FGMs, and the simplest process that can be used for fabricating FGMs using powder metallurgy route is the pressureless sintering process. So, in pressureless sintering process, as we know, we do not apply any applied pressure, and typically the process is done at a very high temperature to provide sufficient diffusion of the atoms, and as a result the properties for pressureless sintering components are much low, kind of inferior to the components which are fabricated using the pressure sintering process like hot pressing or whatever. Now, what are the various steps involved in pressureless sintering? So, typically we would take a die. So, first we have to calculate, or kind of using the models I discussed in the last lecture, you have to kind of calculate or specify the individual layer composition. So, basically the first step is that we take a die, a metallic die typically, and then there actually we have, once we have estimated and kind of decided the individual layer compositions, these layers are actually deposited one by one. That means, one layer, then another layer, then another layer. So, whatever has we have decided the layer compositions, these are actually deposited on top of each other, right. So, this way we have individual powder layer mixtures, and once these layers have been set together, we typically use either a uniaxial pressing, which is the most common one, or we can also use cold isostatic pressing to actually make a green body. And once this green body has been fabricated, this green body is sintered at high temperature to obtain the graded composite structure. So, the schematic process is being shown over here. So, as you can see, again we take initially we have to design the layer compositions, and once the layer compositions has been decided, we put them in the furnace and then in suitable atmosphere. So, normally for oxide ceramics like aluminum oxide or zirconia, we can use normal atmosphere, but if it is a carbide or nitrate ceramic, we have to have some controlled atmosphere like argon or nitrogen gas. So, there actually under those controlled atmosphere we sinter it at, and because we are not applying any applied pressure in this process, that typically we need to go to pretty high temperatures for the to obtain the sintered components. But again, even after one drawback of this process is that because of no applied pressure, we tend to go to much higher temperatures, which is much economical, because if we want to have a combination of both high temperature and pressure, like in for example vacuum hot pressing or spark plasma sintering, the process cost becomes much higher. But in this case, because you are not applying any external pressure, the cost of the process is much lower and you can do at much, but at the same time, because you are not applying any pressure, we tend to have much higher temperature and also for a longer holding time. As a result, we typically have to have, this after pressureless sintering, the samples typically have much larger grain size, which have poor mechanical properties. At the same time, because we are not applying any external pressure, the pressureless sintered components typically also have much higher amount of porosity, and which can also reduce the mechanical properties. So, typical examples or microstructures of the samples which have been fabricated using pressureless sintering are shown over here. So, the top diagram, as you can see, this is an FGM with tungsten carbide cobalt as one side and nickel as on the other side. So, again you can see the gradation in the structure is very clearly visible. So, on the right hand side you have pure nickel layer. So, that means again the aim was that, as you know, nickel is a much ductile because it is an FCC in nature, it is a soft material. But as we go to more harder materials like the cemented carbides like tungsten carbide cobalt, so this is a much harder layer, but because we are joining them by pressureless sintering and the layers were put one after one above another before the sintering process, this is a very effective way, and we can again see that the interlayer regions, like these regions, whatever the interlayer regions are there, all those regions are kind of pretty defect free, and there is a gradual transition from one layer to another layer. And this kind of composite, as we learned in the last lecture, it is a discretely graded FGM composite. So, once again, the composites or the FGMs which we fabricate by centrifugal casting process, these are continuously graded FGMs because they are, although the gradation is there, but still the gradation is kind of continuous gradation, whereas in this case this is a discretely graded composite, because we can see, we can clearly earmark the region over which the transition has taken place. And the bottom diagram, again this is another example where tungsten and copper was used. Again the right hand side you can see the 11th layer as is being done over here, the 11th layer was copper, and the first layer that we see on the very top side, this is again tungsten rich layer. So, again we can see that the transition from copper to tungsten is very gradual, and the overall sample, the thickness was 11.5 millimeter as is being shown in this diagram over here. So, another variant of the powder metallurgy process is the hot isostatic pressing, as you can see here. So, here this has a big advantage. So, heap or hot isostatic is a big advantage over pressureless sintering or vacuum hot pressing, because in this case we do not apply the pressure in an uniaxial manner. That means, if we are using the same process but using vacuum hot pressing, so there, as we know, in vacuum hot pressing the pressure is applied along only one direction, because we have the hot press, that means this is again the hot press chamber, the hot press chamber is there with and there the mold is there, in the mold the sample is there, and there the pressure is always applied in one direction. So, this is the vacuum hot pressing. So, now because of this uniaxial pressure application, there can be some density gradient inside the structure, and that will actually have poor mechanical properties. However, in hot isostatic pressing or heap, as you can see in this schematic diagram, the pressure is applied from all directions. So, typically it is being used under gas pressure like some argon or nitrogen gas pressure is used, and this container is kind of, it is a very flexible container, and because of that we have much higher amount of densification, and the properties of the final component, be it an FGM or a final or a monolithic composite, it's much improved than a typical uniaxial pressing in vacuum hot pressing or in any other such process. Another very new technique or very advanced technique which has commonly been used for fabricating such graded composites is spark plasma sintering. Now, spark plasma sintering is again a powder metallurgy process. It is kind of an advanced powder metallurgy process where we apply both high temperature and pressure, and the pressure is applied, again it is an uniaxial pressure application, and the high temperature is basically developing because of the current which the direct current which flows directly to the die as well as the powder sample, and because of the Joule heating we have the attainment of the very high temperatures, and locally at very local points even the temperature can be very high, and that actually provides both sintering and densification at a very small amount of time. So, typically for vacuum hot pressing we tend to have much longer duration, like around an hour or two, whereas in spark plasma sintering we can have a sintered component, a good sintered component in a very short amount of time, say even 5 to 10 minutes. And this has a very big advantage because we do not have to hold the component for a very long time at a very high temperature. So, in spark plasma sintering one big advantage is that we tend to have much smaller grain size, and that also provides very good mechanical properties, because as we all know, as we have larger grain size the mechanical properties tend to be inferior. The schematic of the process is also shown again over here, and again the basic process is again similar as for any powder metallurgy process. So, we have here two options. One option is that we can first prepare the die with the graded component as has already been shown for the previous sintering processes. That means, we first prepare the die. In the die we put the layers on top of each other, then apply the cold pressure to obtain the green body, and then this green body is brought into the SPS chamber, and there it is sintered together. Another variety is that we do not use the previous green body fabrication, and here we fill the graphite die. So, in SPS we always use a graphite die, and this graphite die is directly filled with the powders in a layer wise fashion. That means, as you can see again, and then we apply the pressure and temperature simultaneously to have the sintered component. And again this component on the right hand side, these samples we discussed in the last lecture. So, this is basically the graded component of aluminum to silicon carbide, and this sample was fabricated by spark plasma sintering. So, again it is a 4 layered component as I discussed in the last lecture. So, the layer composition is kind of in the 4th layer we have pure aluminum, and as we move from the layer 4 to layer 1 we have continuously increasing silicon carbide content, and this gradation actually provides high hardness on the surface of the first layer and very high toughness because it is pure aluminum on the surface of the 4th layer. And this sample, this was fabricated using spark plasma sintering, and as you can see in the micrographs of image B, as you can see there is a very uniform gradation of the structure from 1 to 2 to 2 to 4 and this way. And we also have there is very the interlayer regions are very unique. There is kind of a smooth transition, and also the whole structure, because the spark plasma sintering was used, and because it is a very advanced and high quality sintering technique. So, we do not have any pores inside the sample. So, it is a very high quality sample which was fabricated by SPS using powder metallurgy route. Another example where again these tungsten copper samples have been fabricated by FGM. Now, these tungsten copper samples have been very routinely fabricated using such techniques for FGM fabrication, because as I discussed yesterday, these tungsten copper samples are extremely attractive for fusion reactors, because in the fusion reactor the plasma facing component of a fusion reactor, this requires the material should have extremely high melting point. On the other hand, the back side of the sample should have extremely high conductivity to kind of dissipate the heat, and that is why on the plasma facing side we should have tungsten is a very attractive material for that, because it has a very high melting point, and because copper has a very high conductivity. So, copper is a very attractive material for the back side of the plasma facing component. Now, this the joining of this tungsten to copper, or kind of making an composite of tungsten and copper, is very difficult, because tungsten copper has very different thermophysical properties, and also copper and tungsten have almost zero mutual solubility. So, in this case again spark plasma sintering was used, and you can see that it is a very nice structure, almost 7 to 8 layers were fabricated, and the composition varying from pure copper to pure tungsten. And again we can see in the SCM images there is a very nice transition from one layer to another layer, and also the interlayer region is the most important point, because if there is any defect in the interlayer region, that might initiate failure from that point. But we can see in this FGM structure is a very smooth transition from one layer to another layer, and the interlayer regions are very clean, and this is a very high quality material with nice properties for the potential fusion reactor applications. Another technique which is very commonly used for FGM fabrication is friction stirred processing, and this process is actually a variant of the friction stirred welding process. So, what is basically done over here? It is a solid state processing route. It is unlike the melting casting route we discussed until now. It is a solid state process. So, what we do typically here is that here actually first a groove is made. So, basically you take a metallic component like maybe an aluminum block or whatever, and in that you first create a groove over here. So, a groove is created, and then in that groove we actually pour the ceramic powder or the powder mixture, and then we use a tool, and this tool is actually, it is a very highly precise tool, and this tool actually rotates at a very high speed as it moves from or traverses from one side to another side. And then as this tool actually rotates at a very high speed, it actually creates lot of friction between in the groove, and because of this friction the metal actually, because the friction is very high, and because of the friction is a very high amount of heat generation, and because of that the metal softens and plasticizes, and then actually the whatever ceramic particles have been poured over there, this gets mixed with the metallic layer, and once the tool actually traverses the part, again the metal again kind of hardens, and we have a graded structure. So, again we can see a very nice gradation structure is there, and the advantage is that because it is a friction stirred process, so that means it is a solid state process. So, we do not have very high amount of shrinkage, and all those defects are there, and also the microstructure is very homogeneous, and also we have very good kind of transition in the mechanical properties. Finally, the new technique of additive manufacturing has been very popular for FGM materials, and as you know, this AM is a very it's a novel technique or a new technique, where actually we first prepare a 3D CAD model of the component to be designed, and then once this CAD model has been designed, the material to be deposited is kind of put in a layer wise fashion, and then once one single layer has been deposited, the tool or the table on which the component is being built, it actually moves down by certain amount, and then the next layer is deposited, and this way the whole component can be designed in a very in a systematic fashion, and this has many advantages over the conventional processes. Like we do not have, it is a mold free process, it is a free from design, because you do not need any mold for this process, and also we have very less amount of material rejection, and also AM can also fabricate the component in a very short time, and also there are many variants of the AM process. I mean, when initially it was only designed for the polymer components or metallic components, but nowadays even ceramic matrix composites can be fabricated using the AM techniques. There are different techniques are available depending upon what kind of process can be will be used, like direct energy deposition or selective laser melting. So, all these techniques can be used, and the schematic of all these processes are being shown over here, and these AM techniques have been very commonly used in the recent years for fabricating different FGM samples, and some examples are being shown over here. So, you can see that even macroscopic samples like large samples can be fabricated, and these samples can be have a very smooth and smooth transition from one layer to another, and also having very nice structure devoid of some defects or pores, and that is why having good mechanical properties. So, finally, we discussed in this lecture around 6 to 7 different processes for fabricating FGMs, starting from centrifugal casting, then pressureless sintering, then hot isostatic pressing, then spark plasma sintering, friction stir processing and additive manufacturing, and these processes have different, individual processes have their own limitations and advantages. For example, if we take centrifugal casting as one technique, so it's one big advantage is that it's a very low cost process. So, as we mentioned, it's a very the equipment required is very simple, and also we don't require any special atmosphere, and also we can have very large samples. So, the main advantage of centrifugal casting is that we can have it's a low cost process. The final properties are also pretty good. The part size that you can have we can have, it's a very large size. That means typically for powder metallurgy process we have always a size limitation, because as you go for spark plasma sintering, typically around 30 millimeter or so, but more than that it's difficult to obtain such samples, because it becomes very expensive process. But in centrifugal casting you can even have macroscopic samples, like even diameters like 100 millimeter or even higher. Those samples can be made routinely. Also but there is one big limitation is that in centrifugal casting we have the reinforcement content is typically limited, because in centrifugal casting, as I mentioned, the fast process is that we have to stir cast the composite melt, and in stir casting we always have a limitation of up to around 10 to 15% reinforcement content. If we have more than that, then there is kind of reinforcement agglomeration, and those things will reduce the property. So, this is why in centrifugal casting we do not have a very wide variety of or wide range of reinforcement content, whereas in powder metallurgy processes we can have a huge variation in the reinforcement content. Like as you have seen, we can even have one side like 100% of one phase and the other side as 100% of the second reinforcement phase. Those techniques are also not possible in the centrifugal casting process. Another thing is that in centrifugal casting it's a continuous gradation. That means the gradation that we have, it's not a discrete gradation. That means the gradation is kind of more random and not as programmed as for most of the powder metallurgy processes. Now, all these techniques have their own limitations, but each of them are very efficient in fabricating the FGMs for many applications. So, to conclude, in this lecture we have seen that several techniques can be used for fabricating FGM samples. Among them, the pressureless sintering is a very advantageous technique, because this provides kind of an easy technique for powder metallurgy samples, and it can be used for fabricating ceramic, metal and metal FGMs at a very low cost. But one drawback is that because we are not applying any pressure, typically we have to go to much higher temperatures for a longer holding period, and that might actually provide provide large grain size and reducing the mechanical properties. Also, there can be higher amount of porosity in the structure because the samples are not sintered under applied pressure. SPS is another advanced sintering process for powder metallurgy, where we can have very advanced composites, high quality composites, and also fabricated over a very short amount of time, and these also have very good mechanical properties. Also, we learnt about techniques like friction stir processing and additive manufacturing. The main references which were used for this lecture are being shown over here, and yes. So, with this we come to the end of our course on composites and cellular materials, and I hope that this course was beneficial to you. We discussed about many aspects. We started from the aspects of material selection, and then we learnt about the basics of fabrication, and also like we started with composite materials, and then we moved on to foams like metal foams, polymer foams, ceramic porous ceramics were discussed. Also, we discussed about the applications of different ceramic materials and composite materials in detail, and finally we learned about the mechanics and properties of those composites and cellular materials in broad detail. And I hope that you have learnt a lot from this course, and it was a great experience for us to teach you this course, and I look forward to interacting with you more during the online sessions. I wish you all the best, and thank you very much.